In this video we're going to look at the conjugate points on a catenary. So we'll start off with the catenary curve there. Now if you're unsure where this equation comes from, I've derived it in a previous video, so if you click on up here, just up there, then you can get through and look at the derivation of this. Now what we'll do is we'll pick a point on the catenary, so there's a point there, call it A dash, and we'll also look at the gradient of that point. So that's the gradient of that point, so that just moves around and the black line gives you the gradient at that point. Now we'll pick a second point on that same line and we'll call it B dash, and again we'll look at the gradient at B dash. So that again just moves round about. Now we're not, after the graphical representation has been shown here, we'll go through the mathematics and we'll derive what follows, but for the moment we're just going to show you how we can find the conjugate points geometrically. Now what we can do is, if we position both the gradients of the point A and A dash so that they cross over at that point there 0, so they're crossing over on this line here, so this line here is the x-axis. Now the x-axis is the directrix of the catenary, so it's going to cross over on this directrix. So that means that these points A and A dash and B dash are going to be conjugate points. So if I was to move this point B up a bit, so if I move that up to here, okay, then the conjugate point to this point here would be this point here. Okay, so you see the both of them meet on this x-axis. So that's a geometric way of finding the conjugate points. But one thing that we can notice as well, and we'll go through it in the derivations and what follows, is that there isn't just one catenary that will pass through 2 points. You can actually find two catenaries that will pass through the points. Now only one of them will actually exist in reality, and the other one won't occur. So let's have a wee look and we'll show that just now. So if we pop these back to, let's say we pop them back to this point here, okay, so it just needs to be exact, so that's it there. Okay, so now if I pop on another catenary, let's see that catenary there. Now you notice this one here, this one will pass through this point here. Okay, so we can give these points a name. Let's have a look and see if I can find them here. So let's see if we're going to put in label A, that's point A, and we're going to have a point B as well. Okay, so that's point B. Okay, so I'll take this off. I think that I don't want that one in there. Yeah, we'll leave that point B, label point B. So that's, we'll call that point A and point B. So that point A and B, there are actually two curves that will pass through that point, which will be catenary. So the green one will pass through, and also the black one will pass through. So then the question is, which one of these curves actually represents a stationary point which has a minimum? Well, what we'll do is we'll put in the rest of the conjugate points here. So let's look at the other conjugate point as a point B. Let's see where we're going to get A dash. There we go. A dash. Okay, so now you can see that this point A dash is conjugate to B dash. The A double dash is a conjugate to B double dash. Okay, now if we're wanting to find out which one of these actually will represent the catenary of say a hanging rope, then we can note that in the bottom representation here, the bottom curve, you'll notice that the point B is out with the conjugate point B double dash. So we know from what we've said previously on previous videos that in that case the conjugate point here lies within the limits A and B, So therefore that will have a stationary point, but it won't be a minimum or a maximum. Whereas the top curve here, we have our point A and B, and our point B lies within the conjugate point B dash, so B dash there is outside of that point B, so we've got to go through B first in order to get to the conjugate point, as opposed to this one here, we've got to go through the conjugate point first in order to get to B. Okay, so the green curve will not exist, and the actual curve that does exist is the black curve. Okay, now we will get through a derivation of that, and you'll be able to see that in the next section, which we go on to, which will be just the derivations of what we've seen here. Okay, so let's also have a wee look at this here. Now this here is going to be the function which is going to decide, we'll actually derive this function here, and this function here will give us the x coordinate of the conjugate point, and you'll be able to see that as well, because as this value here adjusts, then I could put a line down from this conjugate point and that conjugate point down. Okay, so let's just draw the lines down so you can see. There you go, there's that one there and that one there. So now if I was to move this along, I'll get to a point here. Okay, you notice at that point there, in this function, the crossover point, or the root of that function there, is the x coordinate of that conjugate point, and it's x coordinate of that point there. Okay, and these 2 points are conjugate. So if I was to move this curve into a different shape, then all that would happen is that this curve here would move, and the x components here would give us the x components of the conjugate points. Okay, again, we'll see that whenever we go and do the derivation. So I hope that was of use, and it's a good lead in for what comes next. If you enjoy these videos and you find they're useful, then don't forget to subscribe or leave some comments, and I hope you enjoy the rest of the maths. So what we have here is the equation of a catenary. Now if we were to draw one out and take a point A, which is minus hk, and B, which is hk, then we'll notice that the value B just shifts it left and right. So if B was equal to 0, then minus h would equal plus h, and we would only have, we'll be left with the equation y equals k cos h upon c. So if we were to then redraw that, and if we were to write k upon c equals cos h upon x, and then replace h with cx, then we'd be left with two equations. The two equations would be y cos x and y equals kx upon h. And if we were to draw both of those out, you'll notice that there's an angle alpha between those. So if k upon h was less than tan alpha, there would be no solution. If it was equal to alpha, it would be one solution. If it was greater than alpha, there would be two solutions. So there is possibly two solutions to this problem. So we've already seen in the graphical calculator that there are two solutions to this problem for case number 3, and you'll notice that the two solutions will give us two sets of conjugate points, A dash and B dash. Now solution number 1 will note that the conjugate point A dash lies out with the limit AB, so this is going to give us a stationary point, and it's going to have a minimum or a maximum value. But in option number 2, you'll note that the conjugate point B dash lies within the AB limit, so this is going to give us a stationary point, but there will be no minimum or maximum. So we've alluded to that already within the graphical calculator. So let's look at this analytically. We've got our equation y equals cos x plus b upon c, and we're looking to look at partial y by partial c by partial y by partial b, and we'll need to go through and do those derivations. So the partial y by partial c has just been done there, and now we look at partial y by partial b, and then When we've worked those out, we're going to divide those out and we'll get this equation here. So this is going to give us the position of the x coordinate of the conjugate points. So I'll just write it out in full again. So that's what you'll see in the book by Charles Fox, the Introduction to Calculus of Variations. So we're not going to look at this any more analytically. What we're going to do is look at a geometric interpretation. So if we take the catenary here and with the directrix, and we notice that if we have a value for b, then it'll be offset by the centre by a value of b, and the distance from b up to m will be our value for our x. And if we were to take a point pxy on that and draw the tangent down, it would meet the curve at point t. So then you can say that tm upon mp would equal the 1 upon tan mtp. So then tp would equal mp upon tan mtp. So that would be equivalent to the equation here. Okay. So then you could say that ut upon c equals um minus tm upon c. So it means that we have x plus b minus cos x plus b upon 2. Okay. So the tangents to the conjugate points would therefore meet on the directrix as seen previously.